Hello everyone. Let's discuss LDA, which stands for linear discriminant analysis. The idea is to find a proper projection or transformation, maximizing the separability of different classes. Assuming that you have dependent variables being multiple classes, right? Just like in logistic regression, you have binary variables, or potentially you have multiple classes. And then is it possible that we transform the original data so that we are able to easier to separate the original data into different classes? That's really the idea. So now let's use an example. We have n data points, xi, yi, and m dimensions to see that there are m different variables of x. And then the yi belongs to k different classes. In a simple case, let's start with k equal to 2. Essentially, yi can belong to either class 1, C1, or class 2, C2, for example. In the case that y is 0 or 1, then it's binary class for the dependent variables. There are n1 data points belong to C1 and n2 points belong to C2, n1 plus n2 equal to n. So we have n observations, and each one of them have m dimensions for the x variables, and then for y you have two classes, C1 and C2, and then for the first class it has n1 observations, second class it has n2 observations, and then n1 plus n2 equal to the total number of observations of n. So we can define mu1 being the mean of the variables. So mu1 being the mean of the variables So here you can see, because we have xi, this I is the ith let's say ith observation, right? So because if you remember, we used so here it's a little bit slightly different from what we discussed earlier, in the sense that we have m variables x1 all the way to xm, and not m variables, and then each one of them has corresponding observation of n data points, so that this I stands for the ith observation. So you can calculate the mean of those two different classes of each of the ith observation, especially for the ith observation that actually belongs to the first class C1. And then once we get that mean, mu1 and mu2, we can leverage mu1 and mu2 to calculate the variance or covariance matrices based on within cluster variance. So let's think about it this way: as simple as you have two clusters of data, C1 and C2, or two classes. Two classes, we can leverage this classes information to separate those two sets of data. In other words, in data mining language, we call it two different clusters. In order to do that, what we need to do first is to calculate the mean. If it's just one variable, as simple as calculate the mean of the first cluster versus the second cluster. They would have different centroid or different mean. And then you use the observation for the first class in the first cluster, use each observation minus the mean, calculate the variance within the cluster variance of the first cluster. Same thing for the second cluster, which would be the S2 that we are calculating here. Once we have those two elements, mu1 and S1, and mu2 and S2, we kind of get a sense on the cluster summary, right? Where is the centroid or where is the mean, and what is the variance of the data points? Let me actually use some example here. Let me see. Let me find some tool to help us. Okay, I'll leverage this space instead of so I already used this red and green to separate those two classes data. The first thing you want to do is really that to calculate the mean of different class. The first, for the green dots, where is the mean? The mean is somewhere here, right? You can get the mu1, that's the idea basically. And then you can get the mu2 as well. Next thing is, how about the variance within this mu1? Within this class 1 and the variance of class 2 of all the observations. So each individual point, the relationship between each individual point, and let me use a different color, and the mean, how far, right? I'm just using the distance, but the idea is get within cluster variance. So that's really a summary of this distance, basically. That within cluster variance S1 is a summary of the relationship between individual observations and its centroid or its mean. Same thing for the other one for the red, so that now you have mu1 and S1 to help you to understand this cluster, and you have mu2 and S2 to help you to understand this cluster. So here I give you more detail on the objective that we are trying to objective function in the LDA that we are trying to maximize or minimize. It's really maximize. Okay, so we should first we can estimate the means for the model predictions based on the each of the y in that cluster. Okay, so I actually erased that what we just come back with. Actually, I was thinking there are more that we can discuss on that chart. So I'm thinking let's do it again. Actually, oh, I can go back. I think. Unfortunately, I can't. hang on. Maybe I'll continue with that thought in a little bit. So in a little bit. So what I really want to see is this. As a start, right, when you have the data, you really don't know the label. You don't know if it's red or green. So essentially, the algorithm itself starts with some sort of heuristic, right? You have to assign some of them to one class, some of them to the other class. That's for clustering, but here, because we already have a label, so it's okay, it's okay. My bad. Let's continue with this discussion, actually. Let's continue with this discussion. We already have a label. In this case, it's not quite the same as clustering, but it's already belongs to this different classification. So we can calculate the model predictions, mu1y and mu2y, based on WT, W transpose of mu1 and W transpose of mu2. And then you can calculate the within class variance by doing the same thing, get the within class variance, which comes back based on S1 and S2, as we just discussed. You have a means of the model prediction, you have the within class variance, and then what we were trying to do in the LDA algorithm is trying to maximize the distance between the predicted y for those two different class. So we're trying to maximize the distance, but meanwhile we're trying to minimize the within class variance. Again, we're trying to make sure that those two classes are separable and separate as much as possible. Meanwhile, make sure that within the class variance is as small as possible. Then we can put those two together and come back with a new objective function, which is the mean in the numerator and the variance, which is identical to this in the denominator. So if we maximize this and minimize this, as a result, this FW should be maximized. So we're able to maximize FW as an objective function, and this can be solved by the optimization techniques. That's our LDA objective. Let's use this as an example. And here we didn't actually get into too much detail how it is solved, but at least you should know the output. The conclusion is the weight matrix that we can use is a function of mu1 and mu2 and S. S is a covariance matrix that we discussed earlier, which is a measure of the within cluster variance. And then mu1 and mu2 are the mean of each class. So that's a weight. And then once you have that weight, we're able to calculate a lot of stuff, right? Calculate a lot of stuff, the predicted mean and all of this. Okay, so this is an example. Suppose that we have 12 data points, 6 belongs to one class C1, 6 belong to C2, so that we have N1 equal to 6, N2 equal to 6, N equal to 12. And their data points look like that. XC1 has these observations and these observations. The second cluster, it has classification cluster, same thing. It would have those observations. Now we can get the mean of those two. The first one has mean of this, 2.1, mean of all of these observations, 1.7, and mu2 is 7 and 5.5. Then we can calculate the covariance. Covariance would be the same thing as xi minus mu, and then the way that you can calculate the variance. So the covariance is S1 is in this matrix form, S2 is in that matrix form. And then using N1 S1 plus N2 S2, so we would come back with the S. Once we have the S inverse times mu1 minus mu2 would be our W, which can be normalized by W divided by W norm, comes back with WN, which is the direction that we negative this, negative that, which is the same as positive, it's the same direction, which is the direction onto which the data points should project so as to give the maximum separability of the two classes. Now, just as a closing, just be aware that LDA and PCA can be very effective for any pattern, many applications such as pattern recognition. Okay. I'll stop here for LDA. We'll come back again to continue our discussion on ICA and SVD. Thank you.